In this video, I'm going to describe to you and demonstrate how the digital twin definition language works. By the end of this video, you'll be able to create complete digital twin models of complex physical objects and visualize the graphical connection of their instances. I'll start by taking you through the basic concepts of DTDL, discuss the Metamodel classes used to build a digital model of a physical entity, discuss concepts like semantic data, custom metadata, and historization in DTDL. And then I'll show you how to build a complete model of a bottling plant and visualize it. My name is Kudzai Teresa. Welcome to Industry 4.0.tv, a channel where we regularly publish tutorials to help you master industrial Internet of Things. So if you don't want to miss out on any of the latest IoT technologies, then make sure to subscribe to this channel. A digital twin is a virtual representation of a physical object, process, or system, such as a car, an aeroplane, a building, a temperature sensor, a factory, or the actual production process inside a factory. To help you create digital descriptions of physical assets and systems in a standardized manner, Microsoft developed and open-sourced the Digital Twin Definition Language, also known as DTDL. DTDL uses a variant of JSON called JSON Linked Data, or JSON-LD. JSON-LD is powerful because, as its name implies, it allows you to link data within JSON objects so as to express semantics inherent in the data. As a simple example, let's consider a JSON object describing the pressure sensor of a filling machine. The JSON object would have data that links to another JSON object with data describing the filling machine on which the sensor is installed. Consequently, the JSON object describing the filling machine would also have a link to the bottling line in which the machine is located. This allows you to hop from data point to data point, linking related information together, hence linked data. Therefore, using JSON-LD, the Digital Twin Definition Language provides a standardized way of not only digitally describing the structure and attributes of physical entities, but also the relationships between them. Now, to enable you to digitally describe the state and behavioral attributes of physical entities, DTDL defines a set of Metamodel classes. In simple terms, Metamodel classes are like digital templates that describe the structure and rules of how to represent different types of elements associated with a physical entity. DTDL is composed of 7 primary Metamodel classes: the interface, property, telemetry, command, component, relationship, and data type classes. First, we will explore each Metamodel class, explain its structure, and give examples of how they can be used to digitally represent elements of a real-world entity. Later in the video, I will demonstrate how to combine these elements into a complete digital model of a complex object. Let's start by looking at the property Metamodel class. The property class enables you to represent elements that don't change frequently or don't change at all. Here is how you would use JSON-LD to define a serial number property element for the filling machine. At type is used to identify the kind of information being described, in this case, a property element. Name is the user-defined name of the element, and schema is the data type of the element. DTDL elements can be of standard primitive types like integer, double, string, and boolean, etc. However, they can also be of complex data types. We shall discuss more about complex types later in this video. The property of a digital model can be read only or read and write. For example, a serial number property would be read only, while the operating speed property can also be written to adjust the operating speed. Now, it's important to mention here that a property of a digital model requires a storage mechanism that will retain the data permanently and allow for it to be updated as required. Next, let's take a look at the telemetry Metamodel class. The telemetry class enables you to describe the data emitted by a physical entity. This is typically a stream of sensor readings or an occasional alert or information message. Here is how you would use JSON-LD to define a flow rate telemetry element for a filling machine. Unlike properties, telemetry isn't stored on a digital twin. And then we have the command Metamodel class. A command class enables you to describe a function or operation that can be performed by a physical entity. A command in DTDL can take inputs and return a response. Here is an example of a command element specifying an instruction to start filling at a specified time. The command returns the scheduled filling time as a response. Next, we have the relationship Metamodel class. A relationship class enables you to describe how physical entities are linked together. For example, our bottling line would be related to a filling machine in that the bottling line contains the filling machine. And a filling machine would be related to a capping machine in that the filler supplies bottles to the capper. Connecting digital twins via relationships in this manner results in a set of digital twins forming what is called a twin graph. A twin graph, sometimes called a knowledge graph, represents physical entities in your entire environment while reflecting their interactions. Here is a relationship element for a bottling line digital model showing that a bottling line has a filler. You will notice that the name is typically used to represent the semantic meaning of the relationship, and the unique identifier of the related target model can be specified. We will discuss more about identities of DTDL models later. However, relationships can be defined with or without a target. Sometimes you might want to define a relationship without a specific target so that the relationship can connect to many different types of twins. Next, we have the component Metamodel class. A component class enables you to describe models that are components of other models. For example, the filling machine may have a camera as its component. In that case, you'd want to first define the camera as a standalone model and then reference it when defining a filling machine. Now, the question is, what criteria do I use to determine a component? If my filling machine has a motor, do I treat it as a component as well? The answer is, use a component to describe something that is an integral part of your solution but doesn't need a separate identity and doesn't need to be reflected in the twin graph independently. If you want your motor to have an independent existence in the twin graph, then you need to represent it as a separate digital model and only connect it to the filling machine using relationships. Here is an example that shows how a camera would be referenced as a component within a filling machine digital model. In this case, schema is used to reference the camera model using its unique identifier. Now that we've described the individual usage of Metamodel classes, how do we then combine these elements into a complete digital model that represents, for example, a complete filling machine? The interface Metamodel class is what you use to enclose all elements of a digital twin model. In other words, an interface class allows you to describe all the elements that make up a complete digital model. For example, an interface of a bottling line model would specify all property elements it has, all telemetry elements it is capable of producing, all command elements it has, all its components, and all other digital models that it is related to. The interface is the top-level object of a DTDL definition, and it is what you start with when defining a DTDL digital model, and then you add other objects inside it. Here is an example interface of a digital model. The context property is used to attach a JSON-LD context to the JSON object so that the file may be processed as JSON-LD. In DTDL, the value of the context property is a URI that points to the DTDL context document, which in this case is DTDL version 3. The ID property is the digital twin model identifier, and it is used provide a globally unique identifier for a digital twin model so that it can be interacted with across different applications, systems, and platforms. A digital twin model identifier has three components: scheme, path, and version. Scheme and path are separated by a colon, while path and version are separated by a semicolon. The type property is used to indicate the type of element within a model. In our case, the type is interface. You can also use the display name property to define a user-friendly name for your interface. Lastly, the contents array of an interface is what is used to enclose all elements or capabilities of your digital model, which in this case is of a complete interface of a filling machine digital model that has one property and one telemetry elements. Now, suppose you have a special kind of filling machine that has, say, a temperature telemetry element in addition to the pressure and operating speed elements. To express specialization, DTDL supports inheritance, whereby interfaces can inherit from one or more other interfaces. You can do so by adding an extends field to the model. Here is an example where a special filling machine extends our filling machine interface and adds a temperature element to it. Here it uses extends to specify the identity of the filling machine model from which it wishes to inherit attributes. Then it simply defines the additional element, temperature telemetry. Now let us look at the data type schemas in DTDL. As mentioned earlier, in DTDL, the schema for a property and telemetry attributes can be of standard primitive types like integer, double, string, and boolean, etc. In addition, DTDL defines complex data types that include array, enum, object, and map. Let's take a closer look at these complex types. First, we have an array data type. Like in any other programming language, an array describes an indexable data type where each element is of the same schema. For example, you could use an array schema for the operating speed property to capture the last 5 speeds set on this property. Here is the serialized array data for the array model definition. We also have an enum data type. An enum describes a data type with a set of named labels that map to values. For example, we can use the enum data type for a pump state telemetry element whereby stopped and running labels for the pump state are mapped to values 0 and 1 respectively. Here is the serialized enum data for the enum model definition. Next, we have a map data type. A map describes a data type of key value pairs where the values share the same schema. For example, we can use the map to reflect the operating speeds of multiple fillers. Here is the serialized map data for the map model definition. Lastly, we have the object data type. An object describes a data type made up of named fields. For example, we can use the object data type to represent a bottle that has been filled by a filling machine. In this case, the filled bottle object has color, weight, and fill level properties. Here is the serialized object data for the object model definition. In addition to its native classes, namely interface, command, component, property, relationships, and telemetry, DTDL also allows for additional metamodel classes through something called feature extensions. Let's look at the data types that are enabled by DTDL feature extensions. Now, in most digital modeling cases, there is a need to represent not only the data of a property or telemetry element, but also the semantics of it. For example, the measuring units. To express a value with a unit, you use what are called semantic types. Consider the following filling machine model interface with temp and length element. To give the elements additional capabilities, you need to use feature extensions. Specifically, to enable semantic types and unit types in DTDL version 3, you need to add the quantitative types context specifier to extend the context of your interface, resulting in an interface that looks like this. First, we added the quantitative types context specifier, and then for type of the temp element, we have used an array that includes telemetry as type of the element and temperature to indicate a temperature semantic type. We then included an additional field called unit with degrees Celsius as the value. Similarly, length is used to indicate the length semantic type, and centimeter is used for the units. Next, DTDL has another powerful feature extension that allows you to designate a property or telemetry as something that needs to be historized. To enable historization, you need to add the historization context extender to your interface. Here is an interface of an example model with the temperature element designated for historization. First, we have added the historization context specifier, and then for type of temp element, we have added historized to designate historization of this element. Next, in the event that you need to add custom metadata to a property or telemetry element, you can extend the context of your interface by adding the annotation context specifier. The value annotation type adds one field to the element, annotates, which allows you to name another property or telemetry that is annotated by the current element. Here is an example of how the accuracy of the temperature reading can be added to an example digital model. First, we have added the annotation context specifier, and then we have added a new telemetry element with value annotation type. The element specifies that it annotates the temp element. Its name is current temp accuracy, and it has a data type of double. Lastly, we have an override extension that can be used to override a property in a DTDL model with an instance value. It's used in combination with annotation extension. Here is an example of an interface of a digital model where the units of temperature telemetry element are overridden. Okay, now that we have knowledge of how the DTDL metamodel classes function, let's go ahead and use it to actually build and visualize a complete digital model of a walking line with a twin graph that reflects the relationships of the models that make up a walking line. First of all, DTDL models can be written in any text editor. The DTDL language follows JSON syntax, so you should store models with the extension .json. Using the JSON extension will enable many programming text editors to provide the basic syntax checking and highlighting for your DTDL documents. There is also a DTDL extension available for Visual Studio Code. Now we're going to create 5 digital models: a pressure sensor model, a vibration sensor model, filling machine model, which is a model that digitally defines a filling machine and specifies that filling machines contain a pressure sensor, a capping machine model, which is a model that digitally defines a capping machine and specifies that capping machines contain a vibration sensor, and a buckling line model, which is a model that digitally defines a buckling line and specifies that a buckling line contains a filling machine and a capping machine. Once we've created the models, we're going to use an Azure Digital Twins instance via Azure Digital Twins Explorer to interpret the models. Now, since Azure Digital Twins does not fully support DTDL version 3 at the time of creating this video, we're going to use DTDL version 2 for demonstration purposes. I've gone ahead and created the digital models. Let's take a look at the JSON files. Here is the complete digital model of a pressure sensor. The model interface consists of 2 attributes: a pressure telemetry element and a set point pressure property element with writable set to true. Next, I have the complete digital model of a vibration sensor. The model interface consists of 1 attribute, a vibration telemetry element. Moving on, here is a complete digital model of a filling machine. It has 6 attributes: a serial number property, operating speed property, flow rate telemetry, liquid temperature telemetry, a relationship, and a command element. The relationship element uses the name contains for semantic meaning, and it points to the pressure sensor model that I showed you earlier. We will see that relationship captured visually in Azure Digital Twins Explorer. The command element is start filling. The request takes number of bottles to be filled, and the response returns the number of bottles scheduled to be filled. Next, let's look at the capping machine model. The model has 4 attributes: a serial number property, a cap size property, a talk telemetry, and a relationship element. The relationship element uses the name contains, and it points to the vibration sensor model that I showed you earlier. Finally, we have a bottling line digital model. It has 4 properties: a date of commissioning property, a location property, and 2 relationships. The first relationship element uses the name contains filler, and it points to the filling machine model. The second relationship element uses the name contains capper, and it points to the capping machine model. Now that we have all our digital models, we can upload them to Azure Digital Twins for visualization. But first, we need to create the Azure Digital Twins instance. To create an Azure Digital Twins instance, you go to your Azure portal, select Azure Digital Twins, and enter your instance details. Then click on Create to deploy your Azure Digital Twins instance. Once it is successfully deployed, go to the resource. On the overview page, click on Open Azure Digital Twins Explorer. Next, we need to upload the JSON files for the DTDL models that we've built, starting with the pressure sensor model, followed by vibration sensor, filling machine model, the capping machine model, and the bottling line model in no particular order. Once you've uploaded your digital models, you can then use the models to create instances or digital twins. Create a digital twin using each of the models, giving them a unique name. For the pressure sensor digital twin, you can see that it allows us to enter a value to update the pressure set point as specified in the model. And the filling machine digital twin allows us to update the operating speed and serial number, also as specified in the model. Finally, we will create a digital twin of our bottling line. Once we've created all our digital twins, we can view the model graph created through relationships. Here you can see that the filling machine and capping machine digital twins are connected to the bottling line digital twin using a contains relationship, and the vibration sensor is connected to the capping machine, while the pressure sensor is connected to the filling machine. And then going back to the digital twins, you can start updating the property values. Of course, under normal circumstances, these would be programmatically updated, including telemetry data. Now, a crucial aspect of DTDL is that you can perform queries against your digital twins using SQL. This is a powerful way of generating advanced analytics for digital twins, and this has potential for many applications in manufacturing and all the other different industries. So this brings us to the end of this video. I hope you found it useful. If you did, please leave a like or a comment below. And don't forget to subscribe to get more videos like this. Thank you for watching.